Alright, so continuing on with our discussion about Chapter 8 and periodic trends, one thing I want to pay attention to is the common charges that elements take on. Okay, we've already seen that we can assign a charge to an element based upon its position on the periodic table. In other words, we knew everything in group 1 had a +1 charge, everything in group 2 would take on a +2. Okay, we said that everything in group 17 would be -1, 16 would be -2, and so on and so forth. What I want to do here now is explain why that's the case. Okay, so if we look at group 1, okay, we said group 1 is going to contain things like lithium, sodium, and potassium, cesium, rubidium, all that stuff. I'm going to leave hydrogen out of this for now again because hydrogen's just a little bit on the unusual side, because it's the only atom that could actually lose an electron and not have any electrons left. But let's just focus in here on lithium. Okay, we've already said that lithium is going to take on a +1 charge. Okay, now a lithium atom, which is neutral, is going to have an electron configuration of 1s2, 2s1. Now, if you consider that this can also be written as a helium core with an electron in the 2s orbital, what we notice is that the lithium cation is missing that 2s electron. Okay, we take away one electron and we're left with just 2 electrons in the 1s orbital, which means we're left with just a helium core. In fact, we can say that lithium plus is isoelectronic with helium. Okay, and helium, being a noble gas, is not very reactive, so we would expect lithium plus to not undergo any further changes because it now has an electron configuration very much like a noble gas. We see this with sodium and potassium as well. Okay, we know that sodium's electron configuration, when it's neutral, is going to be 1s2, 2s2, 2p, 6, 3s1. Okay, which is the same as having a neon core with an electron in the 3s orbital. So if we take away that one electron to make sodium +1, we're left with 1s2, 2s2, 2p6, which is the same thing as a neon electron configuration. Okay, so we can say that sodium plus and neon are isoelectronic. They have the same electronic configuration. Okay, and the same thing goes for potassium. Okay, potassium versus potassium plus. Potassium is going to be an argon core, 4s1. And when we take away that one electron, we're left with just an argon core. Okay, so this rationalizes why it is that elements in group 1 are all going to want to take on a +1 charge, because each one of them is just one electron away from having an electron configuration that's the same as a nearby noble gas. Okay, we see the same thing happening on the other side of the periodic table. So if you consider group 17. Okay, group 17 is where we have all of our halides. So fluorine, chlorine, then we go to bromine, and then iodine, etc. Okay, now fluorine, we know, is commonly going to take on a negative charge. If we look at the electronic configuration for fluorine, it's 1s2, 2s2, 2p5. Okay, if we look at F minus, its electronic configuration is 1s2, 2s2. We add that additional electron, it becomes 2p6. Okay, so here you can see that by adding that one additional electron, what we're able to do is fill up that outer shell. Okay, so this is the same thing as the electronic configuration for neon. Okay, so we can say that fluoride is isoelectronic with neon. Okay, and we can do the same thing with chlorine and bromine. Each one of them is just one electron away from having the same electronic configuration as the next closest noble gas. Okay, now if we go across the periodic table, we can see this trend play out a little bit. So if we look at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, we call these the representative elements because they're at the top of each one of their respective groups. And basically they lay out the pattern for the way the rest of the group is going to behave. Because remember, going down the periodic table, all we're doing is adding on an additional shell. Okay, so we have the same type of orbital, same number of electrons going down the periodic table. So we already said that lithium was going to be a helium core, 1s1. Beryllium is a helium core, 1s2. Oh, I'm sorry. Let me change that. That's 2s1 and 2s2. Okay, I'm not going to write down the helium core for the rest of these. Boron's going to be 2s2, 2p1. Carbon's 2s2, 2p2. Nitrogen is 2s2, 2p3. Oxygen's 2s2, 2p4. Fluorine 2s2, 2p5. And neon is 2s2, 2p6. Okay, so we can see that neon has no interest in becoming positively or negatively charged because it already has the right number of electrons, because it wants to be 2s2, 2p6, because that fills its outer shell. Fluorine wants to have a negative charge because when it has a negative charge, it has one additional electron and it becomes 2s2, 2p6. Okay. When oxygen takes on a negative 2 charge, that means it has 2 additional electrons, so 4 plus 2 is 6. Okay, again, we become isoelectronic with neon. Okay, nitrogen takes on a negative 3 charge because by adding 3 electrons, this becomes, again, like neon. Okay. Carbon, well, let's skip carbon for a second here. Okay, lithium, we know that can lose 1 electron to take on a positive 1 charge, which is going to give it an electron configuration that's the same as helium. Beryllium is going to be in group 2 and take on a plus 2 charge. So by losing these 2 electrons, again, it has an electron configuration that's the same as helium. We get to boron. Okay, we can lose 3 electrons, so take on a plus 3 charge, and again it becomes like helium. The reason why I skipped over carbon is that carbon can actually add 4 electrons or subtract 4 electrons. So I'll say plus or minus 4. Okay, when it gives up 4 electrons, it becomes like helium. If it gains 4 electrons, it becomes like neon. And I'm not going to say one's better than the other at this point, but it largely depends upon what else is attached to carbon.